Have you ever just looked up at a ceiling or a bridge or a massive skyscraper and just trusted it? Of course, right? We all do. And that trust, it's all placed in one of the most fundamental yet totally overlooked heroes of engineering, the beam. I mean, these are the silent workhorses holding our entire modern world together. So yeah, let's dive in and see the incredible science that's hiding in plain sight. It's such a simple question, isn't it? But the answer is just fascinating. It's not magic, it is pure physics. See, a beam isn't just some passive block of material sitting there. It's an active structure, constantly fighting against the forces trying to tear it apart. And that's what we're going to explore here, exactly how it wins that fight.
All right, to really get how a beam works, we have to look inside it. The second you put a load on a beam, and that can be anything from the weight of a floor to a bunch of snow on a roof, you're basically starting an invisible war of internal forces deep inside the material itself.
That's right, it literally fights back. And it's not just a single, simple pushback. Nope. Instead, every single particle inside that beam is caught up in this battle against different forces. Some are trying to pull them apart, while others are trying to crush them together. This internal resistance is what we call stress. And as you're about to see, there are two main types happening all at the same time.
Okay, so imagine you're bending a thick rubber eraser. You see how the top surface stretches out and gets a little longer? That's tension. And the bottom surface gets all squished and compressed, right? That's compression. Well, that push and pull action together, that's bending stress. But at the exact same time, there's this other force trying to slice the eraser in half vertically, almost like a pair of scissors. That's shear stress. Any beam has to be strong enough to resist both of these at once. And this is where it gets really clever. These stresses aren't spread out evenly. That bending stress, the stretching and the squishing, it's at its absolute maximum at the very top and bottom edges of the beam. But right smack in the middle, it's basically zero. Now, shear stress does the exact opposite. It's weakest at the top and bottom, but it hits its peak strength right there in the center of the beam. Kind of cool, right? So the really crucial takeaway here is that different parts of the beam have totally different jobs. The top and bottom fibers, they're the heroes of bending resistance. The center line, what engineers call the neutral axis, that's the champion of shear resistance. And every other little fiber in between is handling some specific combination of both. It's this incredibly elegant and complex distribution of labor. Okay, so we're starting to get the physics. But how does an engineer take this internal war of forces and turn it into a practical blueprint for a safe, real-world beam? Well, they don't just guess. They follow a very clear, very logical process. First things first, they have to figure out the absolute worst-case scenario. What are the maximum bending and shear forces that beam is ever going to face? Then, they use a formula to translate those forces into a required strength value. Based on that number, they can pick a beam shape. And finally, they do a last check to make sure their choice is also strong enough to handle all that shear. It's a system, all about ensuring safety. Now, this is where the real magic of engineering comes into play. To avoid getting totally lost in all that complex physics, engineers boil it all down to a single, elegant number, the section modulus, or just S. This one number perfectly captures how good a beam's shape is at resisting bending. It's not about the material, yet, just the geometry. A higher S value simply means you've got a geometrically stronger beam. And this right here, this is the heart of beam design. Think of it like a balancing scale. On one side, you've got the demand, all the forces trying to break the beam, which is the bending moment m divided by the material's strength, sigma. And on the other side, you've got the beam's geometric strength, its section modulus, S. For that beam to be safe, the S side always has to be bigger than or equal to the demand side. The strength of the shape has to win. It's really that elegant. So if the whole game is to get the highest section modulus, or S, possible, how does that actually influence the beams we see out in the real world? Well, it explains pretty much everything. Why beams are shaped the way they are, and why we choose certain materials for certain jobs. I mean, just look at the classic steel I-beam. Its shape is pure genius, and now you know why. Since we know the maximum bending stress happens way out at the top and bottom, the I-beam puts most of its material right there in those wide flanges. The thin part in the middle, the web, that's mostly just there to handle the shear stress. It is an incredibly efficient shape that maximizes its section modulus without wasting a single ounce of material. Of course, shape is only half the story. The material itself is absolutely critical. Steel is unbelievably strong and predictable, which lets engineers create those super efficient I-beam shapes with total confidence. Wood, on the other hand, is lighter and a lot of times easier to work with on a job site, which is why you see it so often in simple, solid, rectangular forms. But that doesn't mean wood engineering isn't sophisticated. Oh no, far from it. And here's a perfect example. For really massive structures like arenas or giant auditoriums, you'll see these beautiful, often curved Glulam beams. By laminating or gluing a bunch of smaller pieces of wood together with super strong adhesives, engineers can create these enormous, custom-shaped beams that are both incredibly strong and just architecturally stunning. So let's bring it all back home. From that invisible war of internal stresses to the elegant design formulas, all the way to the specific materials and shapes, it all comes together in the buildings, the bridges, and all the structures we rely on every single day. So now, when you look at a building frame like this, you're not just seeing steel anymore, are you? You're seeing the physical result of all those calculations. You're seeing section modulus, bending moments, and shear forces all brought to life. Every single one of those beams was carefully chosen to win its own invisible war against stress. So the next time you walk into a building, just look up, because you now have the code to understand the language of its structure. The science is right there, hiding in plain sight, and hopefully you'll never look at a simple beam the same way again.